So we will start the Bay Area meetup. Welcome everyone to tonight's meetup. The topic is basically recap papers from this year's SIGIR and the KDD conference. We have 4 presenters. They are Yu, Riddick, Nadia, and Svetlana. To save time, I'll just let them to introduce themselves. Again, so before that, I need to introduce myself. I'm Thomas, working eBay Search Backend. I'm in charge of meetups, speaker invitation. So if you guys have anything, any candidates want to say on the meetup, or want to recommend to speak in the meetup, just let me know. So before we formally start, do we have anyone want to make any announcement? Anyone? Come over.
Hello, my name is Chris. I work for A9, and I just wanted to make a quick announcement that we are looking for engineers in a lot of our different groups across product search, and I'll be here. If anybody is interested, please let me know.
Please one step behind you.
Come on, there's eBay. Come on.
Any more announcement? Okay.
I'm Brian Johnson, and I just wanted to put a plug in for the ACM Data Mining Conference that's coming October 12th. So if you go to the sfbayacm.org page, you can see. But it's related to a lot of the things that people in this audience probably do. So it's a Saturday, October 12th.
All right, let's get started. Thanks.
Okay, so to easily get access to this computer, so if you guys no objection, I will sit here. So my name is Yu Liu. Actually, I work for eBay for the past 3 years, mostly in search science team. I'm currently work for search ranking problems. In summer, around let's say July 28th to August 1st, and several of us in the search science team, we went for Dublin to anticipate the SIGIR 2013. Actually, it's a pretty nice conference. We find so many good, interesting papers, so that's why we want to share with you guys. Actually, we already have one internal search science review meeting for these papers, but I think maybe people get some very good feedback, so we want to share to the larger audience. Okay, so I will start my part of the paper review. Actually, the paper I want to review today is called Personalized Ranking Model, Adaptation for Web Search. The reason I picked up this topic is because the personalization will be the next year's one of the very important projects in our team. So that's why I deliberately pay more attention on the personalization part in the conference. So for the motivation of this paper is searchers' information, they need to be diversified. And we need the personalization for web search. Actually for e-commerce, we also need the let's say personalization as well. And the current existing method for the personalization, generally they, based on this paper, they try to group them into the 2 different types. One is extracting the user-centric feature. Generally we can think it's learned from the past history. So just like when you learn, you generally need data. So we need to get the user's information, for example, location, gender, all the click histories. And generally, if you want to build a feasible model, you need some kind of data, just like you need to have enough large amount of the user history to build a user-specified model. And another idea is based on some paper which published in the WW07. It's based on the memory-based personalization. It's more like they try to link the query with the URL, just like user put some query and they visit the different URLs. They build some graph model for this URL and they try to get some information about the user's interest. So actually they encounter some problem, just like it will be hard to, let's say, generalize, and the coverage is low. So for the majority consideration for the personalization generate a two problems. One is accuracy. So we want to maximize the search utility for each single user. And the other one is efficiency. The thing is that we want to adapt the user's result preference quickly, and we need to make the data scalable, the model scalable. So in this paper, they propose a very interesting idea, so which I like a lot. Just like they want to do the personalized ranking model adaptation based on, let's say, pre-trained global model. So for example, the global model, they use some linear, let's say, learn to rank model. So it's more like they have some, let's say, feature space, and for each of the features, they have some weights. And for the if they want to adjust the generic ranking model, they just need to time another, let's say, adaptation matrix in front. So it's more like they already have some general model. They want to project this model to the different, let's say, directions. So in the paper, they mentioned they want to adapt the global ranking model for each individual users. Actually, this one is pretty, I think to me it's pretty similar like the regularization, because besides the basic loss function, and they add another, let's say, item, and this item is more like a regularization in the regression part, yes? Yeah, okay. So they just want to add this part and try to do some adaptation. And, oh, I forgot something here. Actually, this is a matrix. They try to do the adaptation. But we can see this matrix is not just like it's a full ranked or matrix or something. They try to group the feature together. They have some reason to do that. They want to organize the ranking feature together so the shared information can be processed together. The reason they want to do that, they want to reduce let's say, the complexity of the calculation. So in the paper, they propose 3 different approaches to map the original ranking features to some different groups, some certain number of the different groups, for example, K numbers. And the first one they propose is grouping the features by the name. So for example, for ranking, we have BM25 body, BM25 title, BM25 description, everything. So they just try to cluster everything by some, say, name or the manual crafted patterns. And based on their, let's say, later analysis, they don't find it's a very efficient way. And then they propose another way. It's called co-clustering of documented features. So to me, when I read through the paper, I kind of start to understand this one. It's more like, let's say, it's a feature reduction or PCA. So they use SVD and try to make each of the features more independent with each other. And then they try to group the, let's say, the highly correlated feature together by some k-means clustering approach. And this one, they said it's okay, but it's not the perfect one for their solution. Then they proposed another idea. They called clustering feature by importance. They give the name as a cross. So the idea is they divide the training data set into some, for example, a certain number of the small pieces. And then they train each of the single linear model based on this small piece of the data. And then they build another matrix. For example, the dimension will be the number of the feature times the number of the model. Then they try to group, let's say, the features, still use the k-means ones based on these weights on the different models. So to me, I think I try to generalize this idea. For me, it's more like a neural network. They're adding one hidden layer. So they try to project something, use some kind of the project, let's say, matrix. So let's say based on the neural network, theoretically saying, let's say, when you're adding one more hidden layers, actually they can handle much more complicated information.
One question.
Yes.
So what's the difference between the latent factor or importance in your?
Oh, you're talking about the factor importance in the ranking model, right? Actually, they use you can say it's the ranking model importance is more like the different weights of the, I say, the features, right? So the higher weights, the features is more important, right, in the ranking. But for them, just like they try to group the features, not by the weights, let's say, whether the weights is large or not, they still try to group the, let's say, the features by the, to me, it's more like a similarity of the features. Yeah. Okay, so they bring up this discussion. They think, okay, it's a more general framework for ranking model adaptation. So it is not very hard, it's pretty straightforward, so they can apply to most of the existing learning to rank algorithm. And since it's a model-based adaptation, so we don't need to train each of the personalized model based on the raw resource data. And since when I just mentioned about just like the cost function part, they only add one item in the, let's say, cost function. So it's within the same optimization complexity. So we don't have extremely terrible complexity added on top. And another thing is the adaptation sharing across features to reduce the requirement for the adapted data. So later on, they will show the results why this one is, I say, works pretty well for the user, which we do not have too much data, just like a kind of not a busy user or frequent users. So this is the experiment setup. Actually, they use a bin.com's query log. It's from May 27 to May 31st. So I think it's five days data. And to evaluate the results, they have some manual relevance annotation. So to us, it's more like a human judgment. So they give different, let's say, 5-grade relevance score. And they claim they have 1,830 ranking features, but they didn't disclose all these features in the paper. But to me, I think it's a lot. They only give some examples which known to everybody and no much more information, just like BM25, PageRank, TF-IDF, and something else. So they, they built the user's adopted model against the global model, and the cross lambda rank is something they claimed. And actually, the RA lambda rank is another. I have to say the state-of-art, personalization adoption model. They want to do some comparison. So they separate the user by 3 different types. One is heavy user, and someone, the second one is a medium user, and the last one is light user. The definition for the heavy user is in their training data sets, just like they have more than 10 queries for this user. And for the medium one is between 5 to 10, and less than 5 is some light users. And they built the personalization model, and based on the human judgment data, looks like they claim the cross lambda rank performs pretty better. So actually they use some, maximum, that is a mean average precision, or the precision at rank 1 and the precision at rank 3, and the mean reciprocal rank as the, flags to indicate this one. So they claim they got much better result, especially for the light user. Okay, so here's come to the conclusion part. Actually, they think it's an efficient ranking model adaptation framework for personalization search. And the problem is that they use a linear transformation for model-based adoption. So the transformation share within a group mice. So just like try to save the, the training data. And they also mentioned currently they use, feature group is one step, and then the model transformation is another step. So later on, they want to combine these two together to use a joint step to do this. And they want to incorporate more user-specific features and profiles. So current data, they mentioned they don't have too much user-specific features. It's more like general features. And the current paper only focused on the ranking model, which built by the linear learn-to-rank model. So they want to extend to the nonlinear model as well. Okay, so that's pretty much about this paper. Yes?
So this was all sort of prejudged, human-judged data?
Yes.
They didn't actually run it in front of users?
Yes. Okay. If now that, yes?
So the main problem with personalization is it's very sparse.
Yes, exactly.
How do they manage to verify that?
The ways they claim the approach is very successful. They use human judgment data to say that, but actually for eBay, when we do the presentation, we also have the same problem. We have very sparse data sets, right? So if we want to build, let's say, learn only from the past history, we will have problem. We only can cover small amount of the users, right? So that's why I think this user propose something just like whenever we don't have any data, we build a general model, and we can, let's say, gradually learn from the data we accumulate based on, let's say, limited number of the search or something. So that's another reason let's say I want to review this paper, because they claim they have much better performance for the light users than the heavy users.
I don't understand how that's possible.
One reason is that it could be in session, right?
Yeah.
There's only one step, once they approach, or once they come to bed, and within the same session, they're able to do 5 searches or so on. And, but for cases where there are more searches, let's say more than 50, it could be over a period of a long time, like a month.
No, I don't think they're not claiming that they're doing better for light users than heavy users. They're getting a bigger delta improvement.
Better.
Yes.
So
Right.
Yeah, exactly. They are not doing a perfect job.
They're getting a decent lift off.
Yes, they don't say they got perfect job, but they said compare with existing ones, they have some improvements. And actually, I asked a question during the conference. I said, because this kind of adoption, actually we have some assumption, just like the delta between the general model and the user-specific model shouldn't be too large. Otherwise, you still need a huge amount of the data to adjust that one. They said yes, but they make this assumption.
Yeah, inside
Yeah.
the session, I
Yes.
the session will be much higher because
Yeah.
let's say only for eBay use case, because the user is looking for item in a particular category, you'll be searching for it in the same category itself. If it's on an item, you see the category, then probably is one of the one items just particularly belong to that category. But if you take over a period of 30 days, it could be the category distribution could be searching for items in category A versus B versus C over a long period of time. So it probably doesn't do that big of a delta.
Is it by Microsoft?
Microsoft, actually, it's Microsoft cooperate with somebody in UIUC.
Okay.
Yes. So, okay, I think I need to give the second speaker. Yeah, do we need, I think we have the slides here.
Yeah, but I update them.
Oh, you update. Okay.
Hi, my name is Nadia Vase. I've been at eBay for 2 years, and I work in the search science ranking team. This paper was presented by work done at Microsoft, by Microsoft employees that use primarily Bing as their search engine and as their data. So the big idea is that they have a lot of underperforming queries where users are dissatisfied with the search. But as with any ranking or search engine problem, what do we do with those queries? How do we identify exactly why they're underperforming? And then what do we do once we've identified that? So they have 2 parts to their solution. One is to identify the dissatisfying queries, so the dissatisfying search experiences. And then they cluster those, and then they train a specialized ranker. So they have a cascaded model where they have a general ranker for their search engine ranking and then a specialized ranker. So that's the big idea. It's pretty simple. So one key interesting thing is how they identify dissatisfying queries. They did extensive research, and finally what they discovered is probably their favorite signal for when a user is, determining when a user is dissatisfied was the search engine switch. So when a user is in Bing, they type something, and then they, for some reason, switch their search engine and go to Google. And because they were Microsoft, they could do this because they had toolbar data. So users voluntarily opt in to use the toolbar, and Microsoft collects their data for their search behavior. And not all search engine switching events are indicators of dissatisfying queries, dissatisfying search experiences. So they actually built a classifier to predict which of these search engine switching cases are dissatisfying. They determined that about 60% of those events are dissatisfying, or because the user was dissatisfied. So in their classifier, they just trained they created a binary classifier. There are actually about 5 or 6 reasons why users switch search engines, but the only one they care about is really that the user is dissatisfied. So they trained a binary classifier to determine when the user is switching, whether or not it's because they're dissatisfied or because it's something else. So their classifier was based on labeled data, and it was just a binary classifier using logistic regression. The interesting thing is actually the features that were used. There's a variety of features that are query-based features, as well as pre- and post-switch-based features. So features such as the time difference, essentially the dwell time, and time in seconds between switching queries, as well as features of the query, like the number of words in the query. They also have action dwell time, time-based differences, number of queries in the search, number of clicks, and things like that. So there are a lot of really interesting features that they used. I encourage you to look more in the paper in more detail. Then, with these dissatisfying queries, they clustered them. So the idea is that an individual query, an individual search may be dissatisfying to a user, but how do we identify what characteristics of the search made it dissatisfying so that the ranker can improve? They took advantage of the fact that there's systematic reasons for searches being unsatisfactory, and by clustering, they can exploit the cohesion of the different clusters and identify specific reasons or latent reasons why the query is dissatisfying. So they use different features to, so once they've determined the dissatisfying queries, and they determine that using this logistic regression classifier, and then they have another clustering algorithm which then uses another set of features. And those features are similar. There's query-based features as well as SERP features and search instance features. So query features like the language, the phrase, the type of the query, and they also used, they tried to approximate query intent by using they basically attributed a category using the Open Directory project. They attributed a category to the query. And then they have SERP features. For instance, did the search engine result page have a direct answer? Did it have was a query suggestion shown? Was there a spell correction, etc.? And then they have search features of the specific search instance, like the market, the query vertical, the search engine, as well as time-based attributes. And then they used an out-of-the-box clustering algorithm from Weka, an FP growth, to do the clustering. I don't know, they didn't go into details on exactly how this clustering was done, but basically they just created 140 binary features and then order them by the features that are most common, the attributes that are most common. And then they created these FP trees, these trees that represent the relationships between all the attributes. And then they use a standard clustering approach on the tree, basically this bottom-up approach. It's a little bit vague, but I think that any clustering algorithm can be used here, and it's actually the bigger picture is more important if they use clustering. Okay, so here's some example of clusters of attribute sets. So the attribute sets they clustered to identify the attribute sets were grouped, and that's what gives rise to the actual clusterings of the data. So here's some examples of their most common attribute sets. The query is an English query. It's a local search. It's a navigational query, and the number of words in the query is greater than 10. So there were dissatisfying queries that satisfied all of those characteristics and nothing else, and that was one distinct group of dissatisfying queries. So each of these 4 lines corresponds to a distinct group. And it's not disjoint. Okay, so then once they have these clusters, they build a specialized ranker on top of the generalized ranker, and they use a cascading approach, which basically means that their general ranker, which they use for all queries and all searches, has a large set of features, and it's trained on like 10,000 queries. And then each specialized group is trained, each specialized ranker has the same features as the general ranker, plus one additional feature, which is the score of the data on in the general ranker. And the specialized ranker is trained on the subset of data corresponding to that dissatisfaction group. What this plot shows is basically that they have this metric indicating how much the user's dissatisfaction is correlated with NDCG. And what this shows is that the level of dissatisfaction is, so for example, at dissatisfaction correlation value of 2, the NDCG is around 35, and lower dissatisfaction metrics, the NDCG at rank 1 is higher. So it shows that there is indeed a positive correlation between their dissatisfaction metric and NDCG, negative correlation, sorry. So that motivates the use of their specialized ranker. And so they ran these experiments, and in their paper they presented results for only one dissatisfaction group. And so this case is telling. Their specialized ranker did actually improve NDCG at rank 1, and that was even almost 1.5%. So so that's the main idea. Are there any questions?
So I had a kind of curiosity question just very early on. It said that they have pre-switch and post-switch measurement. So how are they able to monitor post-switch because of the Microsoft?
Yeah, they collect all of their data from the toolbar. So users voluntarily opt in to allow Microsoft to collect their toolbar user behavior data. So, yeah.
How did they decide what was the correct intent of the user? By going to Google comparison, or how did they do that comparison? When they switched to Google, did they know whether Google got the right answer with Google they got the answer, or how did they come to?
They didn't specify whether the users were actually satisfied in Google.
Okay.
Yeah, and they didn't go into detail on query intent as a feature, but they did have, this. They used the Open Directory project and identified some semblance of query intent using classes of the items that are in the top 10 of the SERP, and took that as the class for the query.
So just one Did you mention any numbers on how many cases where the items coming from third page or fourth page were brought to the first page itself for failure? I'm assuming the ranker itself was able to sort of make the dissatisfied query go satisfied by showing the best result out there at the top. But sometimes there is no recall itself. Like the big itself misses the recall and so on.
Not sure about that. In fact, I'm not sure if they even, I don't know if they even tested this on live data. This is, as far as I could tell from the paper, this was just an experiment on offline data.
They don't want to reveal the numbers of
Possibly not. Sorry, one question.
So yeah, so so they take those dissatisfying queries and then they run regular ranker, they get scored, and then they decide whether to run I guess additional I think they used to have a regression trees before. I'm not sure what they're doing now, but are they doing those additional? How do they train? Do they train from scratch for those dissatisfying queries, or they train on top of already trained do they train on all query sets and then do additional trees for the dissatisfying queries, or they train from scratch for dissatisfying queries?
They train from scratch. They have these subset of dissatisfying queries, and that's the training set used for the specialized ranker. And then they use all the same, so for each of those instances, they use all the same features that were used in the general ranker, plus the general ranker's output score for those instances. And then they train a specialized ranker from scratch, but it's the same methodology. It's just different data and one additional feature.
But I have a question that they have the previous presentation, they usually have 2,000 features. So, and I'm assuming this dissatisfying query set is quite small, so I'm then questioning how good they can train from scratch if they have a small query set, training set, and lots of features. So that's why I asked, do they train on the top of something that's already trained? Just do additional training?
No, and that's a good question because I'm not sure what kind of classifier they use. The set that they presented, which gave an improvement, had 2,000 examples in the training set. So they went from 10,000 queries to 2,000 queries. Not 2,000 examples, 2,000 queries. Question?
Can they measure the dwell time on Google search?
If they have toolbar data, I'm not sure what they can measure. They may have been dissatisfied on Google search, but it's not clear that that matters.
At least you know whether they were successful with Google search or not.
Maybe, yeah.
So it's hard to measure any traffic that was issued in the internet browser. So anything, pretty much.
How are they just getting the labels for the retraining or for calculating the MCT and all that stuff anyway? I mean, it was a dissatisfied query, right?
Yeah.
Good. So were they pulling that from afterwards when they, it seems like they had to have gotten that from subsequent search.
I am not sure how they were getting the labels. Yeah, that's a good question.
So how did they generate the training set? So you said there are 5 different reasons why a person goes from Google to.
Yeah.
How do they know?
They have this logistic regression classifier to determine reasons why. Oh, good question. So that part was labeled. So they took those, I think, 500 instances, and they trained a logistic, and they labeled them, and then they trained a logistic regression classifier.
How did they label it? That's what I wonder.
They gave it, so the logistic regression classifier was binary. So they, and the 2 classes were, was the user dissatisfied or not? So it's a deterministic decision about whether or not the user switched search engines. So they took all those cases where the search engine was switched, and then they determined using a logistic regression classifier whether the switch was due to a dissatisfying query.
I understand that, but supervised learning, you need to have the data set which shows this is due to dissatisfaction or not. And how do they determine for each of those training sets?
They went to Google.
But you could have gone to Google, not just due to dissatisfaction.
So the case is they want to Google and clicked on a link very fast.
Same query they type to thereof.
I think they had judges.
All for this query, go to Bing and Google and look at the results and see whether they're satisfactory.
Yeah.
I mean, it's like.
One thing I did not, was the query formatting issue did they realize, or is the back end one? If the query was not formatted, and what was the, anything they identified on their side? Or no? Query, suppose it was posted in different question, different way, it would have got the correct answer even in way, for example.
I'm not sure. I'm not sure if they did anything like that.
Okay.
Another question?
Yeah, so for the 140 binary features, which one had high correlation to the D set?
Oh, good question. No, I don't think they mentioned. Oh, sorry, I'm going into somebody else's slide. Yeah. I think they, if I recall correctly, I think it was this first one that actually had the highest correlation to dissatisfaction. But maybe, maybe that's classified. Maybe they don't want us to know that they're doing very badly on navigational queries. I don't know. Or long navigational queries. I don't know. Any other questions? Okay, then I think I will leave this to the next speaker. Oh, yours.
Okay, so I'm Riddick. I also work for eBay. So the paper I'm going to review today is also from Microsoft. So I think they have the most practical paper in the conference. So the title is Fighting Search Engine Amnesia, Reranking Repeated Results. So the idea behind the paper is, so oftentimes you will, in multiple query user session, so you will end up seeing a lot of repeated results across queries in the session. So the question becomes, if you want to promote those repeated results or demote those repeated results. So given a very simple example, if you go to eBay, you search for something like iPhone 4S, and they assume a cascade user browsing model, which is the user scans the results from top to bottom. Then if you issue an iPhone 4S query in eBay, you get a list of results. And then you think, oh, the first two results are not quite interesting, and you skip them. And then for the third one, you think it's okay, maybe it's a little bit interesting, and then you click on the results. And then you go to the view item page, and you read the description, and think, oh, it's not that interesting. And then you go back to the search, and you reformulate your query. And oftentimes you will see, oh, okay, those top results will also appear in your new query. So in that case, probably you don't want to see them again. So there are two different use cases. One of them is you don't want to see them again. You want to find some new results. The other use case is after a few queries, you still want to find the previous item you clicked. So that's, they define this use case as a personal navigation, where you want to locate the same item again and again. So let's first talk about how repetition looks like in the session. So the logs they use is from Bing search engine, as well as the Yandex search engine, which is a Russian search engine. So there are about 40% to 60% of sessions have more than 2 queries. And among those sessions, 16% to 44% of the session, depending on the search engine, with exactly 2 queries in the session, have at least one repeated results. So with more and the repetition increases with more and more queries in your session to almost all sessions with 10 or more queries. So if you have 10 or more queries in your session, it's almost like 100% you will get repeated results across the results in your session. So the intuition here is just like what I mentioned previously. So they classify those results into 3 classes. If you click on the results, any results above the last clicked result is classified as skipped results, which means the user had already seen those results, and then they choose to ignore them. Probably maybe they are not interesting and they are irrelevant. And then any results below the last clicked results are classified as missed results. And the last category is, of course, clicked results. So the intuition here is you need to promote new results. Those results are previously missed by the user, or those brand new results. And definitely you need to demote the previous skipped results because they are ignored by the user. And for the clicked results, it's a little bit tricky because based on the user intention, you may want to either demote them or promote them. In the case of demotion, if the user doesn't really like to see them again, you want to demote them. And if it's a personal navigation case, just like I mentioned, the user just wants to find the same result again. In that case, you need to promote them. Okay, here's the first plot I want to show. The horizontal axis is the position of the result, and the vertical axis is the click-through rate, the CTR rate. And there are 5 bars in each of the plots. From left to right, different color. It's overall click-through rate, and the CTR for previous skipped results, the CTR for previous clicked results, the CTR for previously missed results, and the new results. So the difference between the 2 plots is the top plot excludes all the repeated results in the session, and the bottom plot includes all queries in the session. The intention here is they want to they want to exclude those personal navigation cases in the first plot, and to include those personal navigation cases in the bottom plot to see the effect of personal navigation in terms of CTR. So the first plot you can see promoting new results, not promoting new results. This is from the offline data, so there's no promotion and demotion. That's the current, you can see this is the current ranking. So the new results have the highest CTR. And then the previously missed results also had relatively high CTR, which means if you tune a new ranker, you'll probably want to promote the new results and the previously missed results. And then you can see the CTR for previously clicked results and the previously skipped results are quite low, which means the user are less likely to click on those results. And the bottom plot, which includes all queries in the session, the middle bar, so at position 1, the middle bar indicated by the blue arrow is the previously clicked results. You can see the CTR for this bar is quite high in the bottom plot, which means there's quite a lot of personal navigation cases once we included repeated results in the session. So for the repeated results, the user issues the same query in the session, they are more likely to click on the same result. And then those bars indicated by the red arrow, the CTR becomes lower, which means, so this bar represents previously skipped results, which means the users are even less likely to click on the previously skipped results for repeated query. So you can safely, I can just say that you can safely demote those previously skipped results because in both plots, the CTR for this category is very low.
Excuse me. So when they excluded like repeated how do they compute like previously clicked results? Like the threshold is then just 1, it's not 2, right?
What's the threshold?
Because like if they included repeated queries, they can see if a person clicked 2 or more times on it, right?
Yeah.
For the same result. But like if they exclude repeated queries from the session, how do they determine that then?
Determine the
Like previously clicked.
yeah.
Is that for the same query previously clicked or the?
Not the same query. So the top plot is for all queries in the session.
Okay.
Yeah, for all queries including the repeated query. Okay. So the same item could appear in different queries, not essentially for the same query.
But the personal one is for the same query clicks?
Yeah, the personal navigation they define it for the same for the same identical query.
The same
and
query.
they click on the same item. And here the CTR, so the horizontal and vertical axis is the same, and then here the CTR for skipped results. So the bar from left to right is all results previously skipped once, previously skipped twice, previously skipped 3 times. So as you can see, the more times you skip the results, it's less likely for the user to click on them again. And here is the CTR for clicked results. So this plot is very interesting. And you can see, so the bars from left to right is all results. Previously click once, click twice, and click 3 times. So if you look at the second bar, which is previously clicked once, you can see the CTR is actually lower, which means if the user has already clicked on the previous on the result once, it's less likely for them to click on them twice. But if you look at the the previously clicked twice and previously clicked 3 times bar, it actually goes up even higher, which means if the user clicks the same result twice, more than twice, it's very likely for them to click them again. So that's a distinguish between if they want to locate the same, so if they already click on the same result twice, it's more likely it's a personal navigation case. The user just wants to locate the same item. If they just click on it once, it's less likely for them to click on them again. So their intention might be, they don't want to see the clicked results again.
Yeah, the assumption here is that the user is clicking on it deliberately. They're not just clicking on something that they don't realize they've already looked at.
Yeah, you can assume that, yes. And then they...
Unless the user has amnesia as opposed to the search engine.
Okay, and then they from the logs they derive a bunch of new features, ranking features, which can help the current ranker. So they categorize them into 4 buckets, as denoted by diamonds, hearts, clubs, and spades. So I can just quickly go through some of them. And like previously clicked, like how many times the document clicked earlier in the session. Previous shown, how many times the result is shown earlier in the session, and how many times the result is missed earlier in the session, and how many times the result is skipped earlier in the session. And then they also generate a bunch of query similarity features, like the maximum n-gram similarity of the current query with any of the previous query in the session, and the average similarity, the repeated results, like how many, if the query had appeared before in the session, and 0 otherwise, if the query had repeated. So, and also the last bucket is the overall stats, the aggregated stats, like the position of the position of the results, the score from here the score is the original score from the ranker, and the total number of clicks in the previous impression of the session, and the dwell time. So for the details, you can look at the paper actually. And then they did some offline evaluation first. The metrics they use is MRR, mean receptacle rank, and MAP. And the model, the new model is called R-cube here. And then the baseline, they have 3 baselines, which one is default, the default baseline, which is the current ranker. And then the second one you can see on the top plot is the personal navigation, which is the default, which is the default baseline plus a position and plus a personal navigation feature, which counts the number of times a particular result has been clicked for the same query previously seen in the session. And then the third baseline is the click history, which is the default, the score from the original ranker, and the position of the item, and the click history, which is basically click the counts of each result on a per query basis. And then you can see the R-cube outperforms all 3 baselines quite significantly on those 2 metrics. And then you can see the bottom plot. It's R-cube plus the historical clicks. So you want to see if the R-cube, because R-cube feature, the new feature from R-cube is pretty much all those in-session user behavior features derived from the offline data. And they want to see if they include the historical clicks, which is the total number of clicks for the query. If they include this feature, it can improve the ranker even further. And it did improve a little bit from these 2 metrics, MR and MAP. Okay, and then they did some A/B testing with live traffic. So interleave results from both R-cube and control. They randomly allocating each result position to R-cube or the baseline. So it's kind of intermingling the results, R-cube and the control. And then once the user click on one of the results, they credit the click to the corresponding ranker. And then they credit the query, which had the most click. And they tested on 5 days data in June 2012 with 370,000 queries. So the R-cube ranker was preferred for 53.8% of the queries, which is higher than the current ranker, and it's proved to be statistically significant. So I think I personally quite like this paper because it's very practical. If your infrastructure supports this, if your infrastructure supports the in-session data, then you can pretty much you can try that. Okay, any questions?
So all are within the same session, right? When you say
yeah, within the single user session, not across sessions. Okay. Oh.
Slideshow.
Okay, so my name is Svetlana. I'm applied research in a search front-end research applied group. So I've been here for a year. It's been here just a couple of days ago. And this is a presentation from KDD, which was in Chicago in August this year. And it's not paper from Microsoft. It's actually it's a small advertisement startup, relatively small, called Media 6 Degrees, and they're based in New York City. And so they actually have some new approach. They introduce some like kind of a supervised like clustering, supervised dimensionality reduction approach that I kind of found interesting. And although I'm not like in the advertisement world, but I think this is applicable to kind of different machine learning approaches and stuff like that. So here they actually introduce like who they are, and they actually pretty much so what they do, they have what's called like data partners that let them actually set up their cookies to track actually. So data partners are different websites. They let them set up cookies so they can track actually users like behavior with different campaigns. Campaigns is any kind of advertisement effort for different brands, and they can detect actually user behavior for different brands and then decide whether to put different ads when user visits some other pages. So so these are the problems they actually try to answer. They actually try to say to do like to find actually user who they should target, and what ads to put, where should they put them. And in the advertisement world, there are two different types of targeting. There is targeting called it's like retargeting and prospecting. So retargeting is actually when a user already kind of purchased certain items from a certain brand. So you know actually that user has a history with that brand. So you can actually repurpose that information and show similar ads for that user. But prospecting is actually finding users who haven't interacted with that brand yet and see what is the likelihood of them clicking on an advertisement for a certain brand if they haven't seen that brand in the past, if they haven't purchased anything from that brand in the past. And what this company does is mostly that more difficult problem, which is prospecting, which is like finding new users to show like advertisements for different brands. This is actually the data that they keep for each user. So they keep like information about each visited URL, and they also keep information about purchase histories. And they provide like, as I mentioned before, they have data partners which enable them actually to set up cookies and track user behavior. They actually want to identify people who are likely to purchase actually a particular product, and what they run is actually they run a massive machine learning like a classification in their startup. So they have for each actually campaign they target different brands, and for each brand they build a model. In their model, so how their model look like? Their model actually is like each URL is a feature in their model, and label is binary for each user. So for each user we have URLs, which are features, and the binary label which says that whether user actually interacted with that brand before or not. And they keep track of 100 million URLs, which is, so it's like it's a very large like model.
And what they were trying to do is actually to try to see whether some kind of novel approach in dimensionality reduction would actually speed up their system. And here they yes?
Just a domain name or it's a full URL?
It's entire URL, as I understood, yes. Here they actually justify reasons for dimensionality reduction. They're very obvious. So when you have a lot of for example, when you have rare events, it's very hard to find positive examples for training, right? So some very kind of not very famous brands and that people haven't purchased very much in the past. So so that's one of the problems. Other problem is they have problem with cold start. When campaign starts, only then they can actually acquire data. So, and that actually cold start problem even kind of makes this rare event problem bigger. And they actually, if model is smaller and has smaller number of dimensions, then they can store it and maintain it in an easier way, which is very obvious. So here they actually just show some examples. So they introduced their approach and then they compared with these approaches. So hashing is very obvious, dimensionality reduction. It's very straightforward. So you have a set of predetermined number of buckets, and you create a hash function and just hash your URL in one of the buckets. It's very straightforward. So the second is categorization. So there are editorial projects on the web, like ODP, Open Directory project, which actually does mapping of URLs into categories. So they use that actually to reduce dimensionality of their model. So instead of looking at URLs as features, they looked at the space of categories as features. And third is SVD, which is a very common approach in dimensionality reduction. So they're kind of benchmarks for what they will compare them later with their approach. And so here is their basic idea. Actually, these all methods that I mentioned before are kind of unsupervised dimensionality reduction methods. So it means that they don't use any kind of previous knowledge about these URLs as features. But what they actually have and wanted to use is actually a very large amount of historical data. So they built actually these models in the past using old URLs, using old dimensions. And from these model buildings, they have actually these model parameters. So for each URL, they have model parameters in each model. And that's kind of historical data that says how much importance each URL had in each model. And they actually want to use that to actually cluster URLs based upon these model coefficients. And so to cluster together URLs that have similar model coefficients in different models. So that's the main idea here. So this is example actually of, so they have a bunch of URLs and they have in model 1 model coefficients for all URLs, in model 2, in model 3, etc. And the idea is actually to cluster these URLs. And they actually chose hierarchical clustering. The distance measure that they chose is so they use Pearson correlation, and then distance is 1 minus Pearson correlation measure. So they actually distance is defined by how much
to URLs are correlated across different models. So if you have any questions, you can stop me anytime. So this is actually the model, the one example that they built. They actually built example for 15,000 URLs, and for 15,000 URLs, they built this like a hierarchical clustering model, so let me just see. So they have like once when they build these clusters using 1 minus Pearson correlation between different URLs. Then the question was how to define cluster using this like they got a tree here. So at which level to cut each dendrogram is like a question. So you can't really cut at the same level entire tree because you're gonna get very uneven clusters, and that's not very good, right? So they actually defined a method to recursively go down the tree and cut actually cut that branch at the point when it covers minimal amount of users who visited those URLs. So, and they defined that to be 1% of all users from the set that they looked at. And so it's a popularity base. And these are like examples what they got like when they did that clustering, hierarchical based clustering. So one cluster is like obviously is like has a topic is like a home. And all these URLs except like American Idol are really like URLs related to the kind of home, have home topic to that. So they set up experiment and they actually took like they built for 28 campaigns. They built like different models, and they had around 4,300 features using this hierarchical clustering, and then they actually tried to set up benchmarks for each of the previously mentioned models. So for hashing, ODP like mapping, and SVM, they tried to actually achieve the same number of dimensions when they do dimensionality reduction. They said for SVD they couldn't actually do anything more than 1,000. They used Mahout implementation of the SVD, and they had huge problems with it, they said. They tried to reduce to 2,000, and it just didn't work out. So they kind of stayed at 1,000 dimensions. So with like with the hash dimensionality reduction, they were achieved. They mapped into 4,300 dimensions, same like a cluster. Commercial is like an open directory project, but commercial categorization. It's not like a free categorization. So it's a mapping from URLs to categories in commercial kind of database. And the free context is like I think it's like a ODP, like a mapping. So this is actually, it's a very common measure. It's actually average lift. So this is like for binary classifier, this is like one of the most common measures. It actually tells you how much your classifiers bear from pretty much like a random classifier. So average lift at 5% tells you at the top 5% of model scores how much you did better than a random classifier. And then so their approach actually had the best average lift at 5% from all other approaches that they introduced, but we have to keep in mind that SVD was only with 1,000 dimensions. SVD usually gives very, very accurate approximations, but the disadvantage with it is you can't run it very, very easily. So that's and then so SVD was like the second best to the cluster. So they actually, all these benchmarks actually did the best. And this is like number of features that they had in each model. So this is like, they struggled with SVD quite a bit. I know the author actually, yes?
Just, this is like a really easy question, but did they say if they were using the SVD implementation now or the stochastic SVD?
They just said SVD. They didn't go into details. So, and then they tried with SVD like all sorts of stuff to make it work. So, and here they were actually, they plotted actually performance of SVD when you vary the number of dimensions. So they looked at average lift at 5% for SVD when you have like 150, 250, 500, 1,000 dimensions. And then they have like two different setups for evaluating models. And I thought that was pretty interesting because one is what they call in vitro. In vitro is like a sandbox. It's like, so their models are, they're advertisement models, right? So they're very much affected with kind of human interaction, like how much money we're going to put in this campaign, how much we're going to bid for each ad. So, so these things actually, they want to actually look at their models regardless of a campaign. So they want to isolate model regardless of a campaign and regardless whether they show that or not, and look how actually user interacts with the brand when ads are not shown. So they want to see how well they're doing regardless of any campaign, how well their model is doing like generically. And they call that in vitro model. And then they evaluate that in vitro, in lab. They actually, their model, so one is their production model, one is a reduced dimensionality model. And it actually does, in average, 15 to 17% worse, which is not bad at all. I mean, it's not like, it's not really bad. And then they actually looked at, in production, they have like a bunch of these models, and then how the advertisement works is actually, there are actually these people who look at the models, they track performance of each, and they say, okay, we're going to bid this amount of money for this campaign, this year. They determine the bid price and stuff like that. So when there is a human actually, when humans intervene with the model, then actually their model is actually does almost as well as the production model. So they actually, so that was the main point. And like if you see these spikes in a graph, you can see those are actually spikes. So like it was a spike there at the end with their cluster model. That's when they actually computed clusters. So they had like a more data and stuff like that. So and that's pretty much it. I don't think they, yeah. Yes.
For three-dimensionality, did they mention anything at all about other approaches like stack model or?
They actually mentioned some of the approaches. They're suitable for the kind of large dimension, kind of binary classifier data, but they actually mentioned why they didn't pursue them, like in a paper. I kind of focused on like their benchmarks, so just to, yeah, but it.
So with that graph that you have up there,
Mm-hmm.
At around the 40% point horizontally, the one, they switch. Is there a story behind that?
Yeah, so the switch here, like, you mean here this spike?
Yeah.
So they have clusters, right? So they recompute them from time to time. And they use the previous data to compute clusters and find new, like, lower dimensions. So I'm guessing, like, that was the time when they recomputed clusters. And that's because that's the base for their algorithm. They cluster URLs, and then they build like models based upon those clusters. So.
Let's give our speaker a round of applause. Thanks everyone for joining us.